Okay, so let's talk about AI and electricity, because if you've been paying attention, you've probably heard two completely different and kind of conflicting stories.
On the one hand, you've got the alarm bells ringing, with people warning that AI is going to melt the grid and basically swallow all of our electricity. But on the other hand, you hear dismissals, people saying the whole thing is totally overblown. So what's the real story? Well, the engineering reality is that both of these claims can actually be true. It all depends on what specific AI job we're talking about. And, this is the really crucial part, where it's happening. The key is to stop thinking about AI energy as just one big single thing.
To get past all the headlines and down to that engineering reality, we need a better way to think about this, a better mental model. And, the most useful way to understand it is to break AI's power consumption into three totally distinct buckets. Once you can see these buckets clearly, all the noise just starts to fade away, and the real picture comes into focus. So let's get into this framework. Think of these three buckets as the tool we're going to use to separate the signal from the noise and finally understand where the power is actually going. Here they are. First, training. Then, inference. And finally, infrastructure. Each one has a completely different power profile. Training, that's like a massive one-time sprint. Inference is the continuous, ongoing marathon. And infrastructure? Well, that's the physical foundation that everything else depends on. And a lot of the time, it's the real bottleneck. All right, let's dive into that first bucket, training. This is the beast. It's the massive, super energy-intensive process of building a large model, where you have these huge clusters of GPUs just running flat out for weeks, sometimes even months. It consumes a tremendous amount of electricity in a very concentrated burst. You can think of it like building a rocket. It's incredibly energy-intensive, it's spectacular, and then it's done. And because it's such a single, massive event, it's really easy to report on. It's a big number. And this is exactly why training creates all the headlines. But it's not the whole story, not by a long shot. So let's move to the second bucket, which is honestly way more important for the long-term picture, inference. So what's inference? It's what happens every single time you or I use an AI model. Every chat query, every line of code it suggests, every image it generates, that's inference. Unlike that one-time blast of training, inference is the constant, always-on demand that just scales with usage. Training might make the 6 o'clock news, but it's inference that creates the monthly electricity bill. But here's the catch. The energy cost of inference isn't some fixed number. It actually varies wildly depending on a few really key factors. For instance, a bigger, more complex model just uses more power. A demand for instant, low-latency responses, like in a chatbot, prevents efficient batching of requests, which also drives up energy use. And of course, newer, more efficient hardware makes a huge, huge difference. This kind of complexity is almost always lost in the headline. And this brings us right to our third and final bucket, infrastructure. This is the physical world constraint. This is where it gets real. Even if your GPUs become magically efficient, you still need the cooling systems to stop them from melting. You still need the substations to deliver the power, and you still need the grid connections to plug into in the first place. This is where the digital demand for AI meets the hard analog reality of our power grid. So with that framework in mind, training, inference, infrastructure, you can probably see why the public debate gets so messy. Most of the confusing claims you hear are making one of these classic mistakes. They'll lump the one-time cost of training in with the ongoing cost of inference, or they'll take the peak power draw of the system and just assume it runs like that 24/7. And maybe most importantly, they ignore geography. A power grid doesn't fail globally, it fails locally. And that's the crucial point. We have to stop thinking about a single global number and start thinking about specific local constraints. So let's try to ground this with some actual data. Okay, for a national baseline, data centers, which, remember, are handling both the huge bursts of AI training and all that continuous demand from inference, accounted for about 4% of total U.S. electricity consumption in 2024. Now, that's a significant slice for sure, and it's projected to grow substantially, with AI being a major driver. But a national average can be really misleading. Because the real story, the one that causes actual power shortages and building moratoriums, is local. See, AI data centers don't just spread their demand out evenly across the country. They cluster in very specific regions where there's fiber and water and land. And this right here illustrates the difference perfectly. On a national level, the impact is meaningful, yeah, but it's manageable. But inside a data center hub, like, say, Loudoun County, Virginia, or near Dublin in Ireland, That new demand can represent a massive portion of the local grid's total capacity, creating very real-world bottlenecks. So the crucial point is that geography is destiny in this conversation. So how can you apply all this thinking? Well, I want to leave you with a practical tool, a simple checklist that you can run any claim about AI's energy use through. Think of it as your own personal signal versus noise filter.
So the next time you see a new statistic, just ask yourself, first, is this number about a one-time training run, or is it about ongoing inference? Second, what are they assuming about utilization? Is it running at peak power all the time, or a more realistic average? Next, what kind of hardware are we even talking about? Also, does the application need instant answers, or can it wait for more efficient batching? And, as we've seen, where in the world is this power being drawn? And finally, is the claim about raw electricity, or is it about carbon emissions? Because, the local grid's energy mix can change that story completely.
So, the next time you see a dramatic headline about AI's energy use, just pause and run it through that checklist. If the claim you're reading can't answer these basic questions, it's probably not a piece of serious analysis. It's likely just an oversimplification. The reality is nuanced, it's local, and it's constantly evolving. And now, you have the framework to see it clearly.